associated with Geminid meteoroid stream. Tony, I'll give you a warning.
Thanks. Thank you very much. And let's go back to that earlier topic. There's a couple good points, actually. The L-Cross near-infrared camera did image Cabeus once it got below the rim. So there, and as Paul was saying, that was mostly scattered light. So you can do sensitive measurements in the infrared, and UVS saw Earthshine all the time when we looked at the backside. So there's a lot of data actually to compare with that. So to UVS, let's see if I can work on this. I'd like to note my co-authors on this. This is a lot of work that's going on in a variety of different directions. It's a very large data set and being very fruitful. I'm going to be really quick on this slide because you've all seen it, and I want to spend time for the other slides here. The UVS instrument was an ultraviolet to infrared spectrometer with rather, for a, depending who you talk to, rather coarse resolution, and that was meant so we get this very large range to do a variety of science objectives. It took measurements all over the place, looking in all different directions, driving mission planners and the spacecraft folks insane, which is a good thing. What I'm going to talk today primarily is about variations around the Geminid showers, and this is kind of in an effort to, one, hone in on one particular event and study it and try to use it as a tool, a guide to understand the data set more broadly. You heard, if you saw Menelaus's talk this morning, that there's a variety of signatures from meteoroid streams throughout the data set, both for sodium and potassium and others, and that's what I'm going to get to at the end of the talk. This shows the noontime observations for sodium and potassium as a function of day a year, and I've highlighted where some of the significant showers are, as well as the red arrows indicate where full moon is. And clearly there's a lot of influence, both short-term and longer-term, on both the sodium and potassium atmospheres from the showers, in particular the Geminids, which really stands out nicely in all the data sets, including the LDEX data set that you'll hear about. And you can see here in the potassium, we see a nice strong peak rate around the time of the Geminids. So this is why we picked the Geminids to hone in on and focus on. It's a clear perturber to the system. This shows another way of looking at the data, both for sodium and potassium. This now shows the sonographic longitude as a function of the column density. This is sodium, and what I've plotted here is the magnetotail entry, blue, and exit, red, just for reference, so you can see where you are with regards to that magnetotail at full moon. And also then, it might be hard for you to see, but some of these dots have little crosses through them. Those are reference to the Geminid shower. As you saw in that potassium in the previous slide, there's a really strong indication of potassium climb at the time. You can see that here during the Geminid shower. So again, this is one reason we'd like to go back and look at it. And also for reference, we overplotted the iron oxide content for these same observations at the surface and the potassium. So again, this suggests that not only the showers are important, but also surface composition as well is very important to these two species. I've highlighted this in the past. It's really nice to be able to put two data sets together from the Kaguya or Selene mission and UVS from LADEE. It's unfortunate we didn't have a full continuous year, but you almost got it with these two data sets. And what's really neat is it does show this long-term trend over time for the two data sets that we are proposing is really a signature of a long-term residence time for sodium associated with the showers here earlier on and late in the calendar year, the Leonids, Geminids in particular. So Menelaus did touch on this morning, and so I won't spend a whole lot more time on this here, except that this long-term trend associated with the Geminids can be reproduced in his modeling, and that's what this shows here. This shows, again, the same sodium data set from UVS. This shows a series of models he's run where he's basically held a constant meteoroid flux, doubled it, and tripled it. And what he's shown, and what he does, he basically puts in an instantaneous pulse for the Geminids over a day or two's time, and you can see it rise here. I think my laser battery is dying. Here it comes up and then it comes back down, very much reproducing qualitatively the data. So we really think we're onto the cause for this long-term sodium trend. And looking at his model predictions, Menelaos said to me, he's like, you're looking at noon because you've got, I look there because I've got the greatest signal to noise for sodium and potassium there, so it's much easier to work with. He's like, but you really should be looking for changes associated with the showers down here before sunrise, because that's where my models predict you see a lot of variation, and this is quite sensitive then to whatever that assumed meteoroid flux is. And so that's what we then went back and did. And to do that, we looked at observations we made during the sunrise. We call these sunrise activity data, real clever. And what the situation is here in terms of geometry is we are in a retrograde orbit. UVS was always looking anti-RAM, anti-velocity vector for the spacecraft. As LDEX and NMS ingested stuff, we looked behind us. And as we went past the umbra and into darkness, we got very, very clean spectra. There's no surface scatter into our instrument. There's no sun scatter then ultimately into our instrument, and we're just staring at the illuminated portion of the atmosphere at the dawn terminator. And this is an example of some of these spectra. Unfortunately, a lot of the shower activity was somewhat early on in the mission. We were really still learning our instrument and tweaking optimization between detector temperatures, operating times, ingration time, and whatnot. But this shows an example of 10 co-added 10-second spectra up here at the top. I've highlighted the sodium and potassium lines with a line fit profile for those two as well. The bottom just zooms in on the sodium band. It's a doublet, and again, we're only at these a little better than a half a nanometer, at these wavelengths, a little better than a half a nanometer spectral resolution, so we don't resolve the doublet at all. But we have about 4 or 5 points across it, and this shows the blue and red lines basically before and after the Geminids, and again, overplotted for reference is a spectral line model using the instrument profile. So we can pull it out of the data pretty easily. Again, this is, these are digital counts. We are looking down here at small counts, and so it takes some co-adding and to get the statistical noise down. But using that line strength then, and I should go back, and the next plot, what I'm doing is I'm just plotting the strength of that line. I take a couple points at the middle of the line, average them together, and I take points to either side, carefully picked so I'm not touching on hot pixels or hyperactive pixels, average those and difference them to get a line strength. Pretty straightforward and simple. And this is what I get for the sodium line strength, plotted now as a function of date. So this is a sodium line strength at just past the dawn terminator. So this is not to be compared with the sodium line strengths at noon. But you see a lot of the similar kind of structure. There is an overall increase during the showers periods. Of course, the error bars here are significantly larger, but there is, I would say, a pretty good correlation between the showers and the UVS data. And to emphasize that, I've overplotted here LDEX impact rate, and that's the red line here, showing the LDEX impact rates. And if I had a laser pointer that worked, there's Geminids. There it goes. Let's back on. Here's the Geminids. You see the rise in sodium here. The torids and leonids are out here. Here's our quadrantids, and it's kind of fun that LDEX, at least in this data set, doesn't show the quadrantids all that well, and that's because they're farther north, about 60 degrees, I believe, north latitude, and that's kind of in the direction UVS is looking, so we actually pick up perhaps maybe the sodium influenced by those showers better than LDEX is able to locally see it. And what's kind of cool too is this shower here that LDEX sees was not, it's a previously unknown shower, they saw it, and we seem to see it in sodium. And actually I was showing Jamie at our science team meeting the other day, I think we see it in the potassium as well. So it appears that this number before a shower might be actually influencing sodium and potassium as well. Comparing then back to that figure from Menelaos' model, looking at the dawn change with time of the at around the Geminids, that's what I'm plotting here, where I'm plotting, basically I pulled a number of strengths at around the Geminids period, and I try to take one well ahead of it and well after it and average it to create a baseline for, meaning this is my background steady state. As you saw in the sodium data, it's kind of hard to do that. What does that really mean? That things are constantly changing. But we're working on this some more, and it is cleaning up a bit better, and it really does show this increase that is reasonably close to what the models might predict. Ultimately, once we clean this up and do a little more work on this, this will help to pin down what the actual impact contribution is to the sodium. What is that flux rate and production rate for the sodium due to the Geminid showers? Once we do that for the Geminids, we're going to do it for other showers, because a lot of these showers are different, both in velocities and compositions, etc. So that will be very interesting to look at. And we've also done some other comparisons looking for other lines. And this, again, was done because, a lot of times you need to focus in on one area and focus on it just to get a result out, because the data set might be too overwhelming. Here, what we did was we differenced a number of spectra that we added from both before and after the Geminids, and I simply did a difference on them after normalization. And what's nice about this is it eliminates most of the instrumental artifacts, which is great. Here I've also scrubbed all the hot pixels, or hyperactive thermal pixels, thanks, Magnus, and removed them here. A third are probably correctable. I just threw them out here. And found that indeed when you difference these, you do see a number of weak lines that are coming up, and then these are weak. This is Rayleigh to the left here. So most of these detections are all below previous detection limits, which are about 10 Rayleigh. What we have been seeing, and I've been very confident in, is the oxygen, hydroxyl, OH, titanium, iron, and aluminum. But I'm really kind of getting more confident actually about the calcium doublet rate in here that is looking quite promising. We have a hard time otherwise seeing calcium at all any other time. And that's surprising, I think, since we think it would be there. So what we can do then is using this kind of as a guide again and developing the line retrieval algorithms to work on these. We can plot some of these as a function of time. And this shows the aluminum line plot as a function of date, also overplotted with the LDEX impact rate. And it actually looks pretty good in terms of a correlation between, again, shower events here. And a couple of them, even this one down here, there's a slight rise here in the aluminum. Don't know what this is, but again, if we need to go back and look at, for example, sputtering rates, Jasper and I have looked at it, don't see anything obviously strong here for solar wind rates jumping here. I'd have to go in and look at the individual spectra. I mean, there's 3 points here, so we have to be a little cautious here. But certainly for the Geminids here, nice strong peak, and also with the toroids and leonids. You also see what's interesting is this overall bulge, again, of the aluminum, kind of matching the LDEX observation and coming down to a baseline background. Likewise for hydroxyl, water, or OH, I should say. Here, again, harder to retrieve for some instrumental reasons. This is using the ultraviolet lines. But we do see generally a pretty good correlation with the LDEX impact rate, actually. Better than I had anticipated. Again, with this higher level of water, or OH, I say water because it could potentially be coming from photodissociation of water, and we can figure that out looking at the data eventually. Higher earlier on during the shower season, if you will, in late calendar year. So in summary, this evidence really is kind of continues to mount that and you heard this earlier in Melissa's talk, that the meteoroid showers at the moon and the surface composition are actually really, really important to determining the sodium and the potassium exospheres, but also clearly other species as well. And I think we've all had hints at this. A lot of the Earth observations are fairly inconclusive with regards to what the meteoroid contribution is. But now these space-based observations, both from Kaguya and now UVS, really, I think, are telling that tale very clearly. And it's going to have to, modelers like Menelaus and others are now pulling that back into their simulations to try to explain these observations. It is pretty exciting that we think we're seeing some of these other species that haven't been seen before. We're seeing them at very low concentrations. Oxygen, the number we're getting is about 10 per cc, so very small concentrations of these things. But again, if we can actually pull them out of the data set and look at them in time, like I've showed you, we can actually better understand the process that affect also other metallic and volatile species, for example, hydroxyl. And with that, I'll stop. Thank you. Data replacement. Good idea.
Yeah, I have a question or a clarification. It looked like when you showed potassium, I didn't see the long-term trend that you saw with sodium. Is that true?
That's true.
Okay, that's interesting.
Uh-huh.
Tony, this is Gordon Chin from Goddard. The OH, other than when you have the meteorite showers, is there a background of OH at the sunrise that you're detecting using this method, the UVS?
It's hard to say within those nodes. You can look at that line and try to draw a background, and it's low. If it's there, it's very low. So I would say if it's there, it's at or near our detection limit, the background. We see it as a sporadic thing that is very much seems influenced by the showers.
But you can't say there's a general background, though.
I can give you I can give you an
you
upper limit on that, and the column is something like 10 to the 8th per cc.
What's the altitude
per centimeter squared?
So what's the altitude?
20 kilometers. We're staring 20 kilometers at the Dawn terminator.
Okay, thank you.
Most of the time, towards the end of the mission, we pointed for about 2 weeks at 10 kilometers, and then the final month we were pointing at 5 kilometers above the surface. Yeah, a little bit, but not much.
Tony, my time in the spotlight. Thank you.